So maybe we start now. So welcome to this OneWorld seminars on imaging and inverse problem. Before I introduce our today's speaker, so let me just make an announcement. The SIAM conference on imaging science is now going on. So here you see on the screen the invited speakers list and also the some of the interesting talks that will be given in during the conference, and I also share the link to the conference, so you are welcome to join this. All the registration fee is free. It's open to everyone, but then you have to register before you can attend any of the talks. Okay, so I'll stop this, and then now I will introduce today's speaker. Today's speaker is Jong Chul Ye. He's a chair professor at the Department of Bio and Brain Engineering and Zheng professor at the Department of Mathematical Science of Korea Advanced Institute of Science and Technology, KAIST, in South Korea. Before joining KAIST, he was a senior researcher at Philips Research Center, GE Global Research Center, both in New York. He is editor to many IEEE and IEEE journals, including IEEE Transactions on Medical Imaging and IEEE Signal Processing Magazine. He is an IEEE Fellow, chair of the IEEE SPS Computational Imaging Conference, and was an IEEE EMBS Distinguished Lecturer. His current research interests focus on deep learning theory and algorithms for various imaging reconstruction problems in X-ray, CT, MRI, optics, ultrasound, and remote sensing. So today he's going to give a talk that is related to this. The title of the talk is Geometry of Deep Learning for Inverse Problems, a Signal Processing Perspectives. Professor Ye.
Thank you very much for the kind of introduction. One second. Okay, here you go. Okay, so can you see the screen?
Yeah.
Okay, great. Yeah, thank you very much for the kind introduction. I'm Jong Chul Ye from KAIST, and it's really my great honor to be here to present our work on the geometry of deep learning for inverse problem. So, as you know, we are currently living in the deep learning ages. So the deep learning has many advantages compared to the classical machine learning approaches. For example, in the classical machine learning approaches, one of the most important part is feature engineering. We need to extract the features to fit into the simple class files. But however, in deep neural network, we don't need those kind of things. Feature can be automatically extracted by the neural network, and then also classifier can be automatically designed. Because of this simplicity, neural network has been successfully used for all kinds of disciplines. For example, I'm working on the medical imaging area, and one of the earliest work is more like using the deep neural network for the diagnosis and analysis applications. And however, the recently new trend of deep learning is actually using the deep neural network for the inverse problem. So basically utilizing the neural network from the sensor data to image formation. In fact, I'm proud that we are one of the pioneers in this area, because actually in 2016, we participated in the low-dose CT Grand Challenges and proposed world first deep neural network approaches. And ever since this work was actually published, and the CT field, the deep neural network has become a more main approaches. And there are a lot of approaches that are now currently available, which can be categorized as many important technical contribution, for example, image domain learning approaches and hybrid domain learning approaches, or domain transform learning approaches, or sensor domain learning approaches. In fact, even actually within very short time period, ever since already the industry take part on this kind of research effort, and then Canon and GE already started to get an approval, FDA approval for the deep learning product for the low-dose CT reconstruction. For example, ACE or True Fidelity is now commercially available by the two vendors. Okay, so Now, when we actually first started working on this kinds of problem, so and when we actually have a very nice result, and one of the first question I got from my clinical collaboration is, yeah, the result looks good, but why deep neural network works for the image reconstruction? Furthermore, they are concerned about whether it creates any kinds of artificial feature. This is especially important for the medical applications. In the medical application, for example, if you create these artificial cancers, it's a very serious problem. It's a little bit different from the computer vision problem. In the computer vision, as long as you can actually generate the cosmetically beautiful images, that's okay. But however, in the medical imaging, you need to actually keep the original data as truthfully as possible. So that means we need to actually give some kinds of idea what's going on inside the neural network. Furthermore, another mystery when we actually come with this kind of deep neural network approaches, actually deep neural network is like a black box, for example. If actually use one of the popular approaches, for example, encoder-decoder structure like a UNet architecture, if we put in the low density noisy images and then train with the clean images, then you can actually generate a very nice result. But with exactly the same network architecture, if we just change the data and put the blurry images and the clean image pairs and then train it again, then you can actually have a very nice reconstruction result as well. And even drastically different approach. For example, image in painting work, if we put the 80% of pixels are missing images and also original images, then the same network architecture can be trained to do the nice mapping. So this is actually very different from the classical applied mathematics approaches. For example, in user method, you need to design a specific algorithm for a specific problem. But here, same architecture works for very different kinds of problems. So the question is why this kind of thing is really happening. So what's going on inside of that? In fact, actually, to understand these questions, you need to actually start with machine learning 101. So we need to actually start with what kind of thing we actually want to actually machine learning model should have. For example, this is some kind of list I can think about. For example, machine learning model should be data driven. So that means the model should be learned from the data rather than the top-down mathematical model. By doing that, you can actually adapt the data very easily. And also, it should be the adaptive model. What we mean by that is, for example, if you actually learn the model, still the model should be adapted in the inference phase depending on the different input. And furthermore, most important part, maybe one of the most important part is the expressiveness. That means actually the model should be expressive enough to actually represent all kinds of large class of functions. So that should be the desired thing. And also, from a computational perspective, it should be inductive in that sense that, for example, if we learn the information from the training data, that information should be used without any kinds of computation again. So that means by doing that, when you can actually save the significant computation time, and that's actually what is required. In fact, actually, based on this kinds of RISI list, we need to actually give some kinds of retrospective analysis of a classical machine learning approaches. For example, let's think about the Kernel machine, like a support vector machine or Kernel regression approaches. One of the famous results in this Kernel machine is the represented theorem. For example, in the represented theorem, now we actually have any kind of loss function, and this is a target data, and this is a function we want to estimate from the input data. And given any loss function and then given large class of the regression term with the Hilbert space norms here, in that case, if you actually minimize this one with respect to some reproducing kernel Hilbert space, in that case, the solution has a very nice form like this. So during the training phase, you are now estimating this expansion coefficient here. And then if you actually have a new data coming in, then this nonlinearity actually generates the different kinds of functions. However, this kind of kernel machine has a limitation from the RISI list we actually mentioned before. For example, the reproducing kernel Hilbert, reproducing kernel Hilbert space is actually compared to the Hilbert space, it's a very small size of spaces. So it's actually the expressivity is limited in that sense. Furthermore, this kind of RKHS, the replacing kernel Hilbert space, is determined by the choice of the kernel in a top-down manner. So depending on the problem, you have some kind of mathematical insight, and you choose a kernel, and then based on that, then you can actually define the RKHS. But however, it's difficult to adapt from the data. Furthermore, if actually train that data, the training data actually generate the estimate the regression coefficient, but this doesn't never change. So if you have a new data, the test phase only changes this part. Now this doesn't change it. So because of that, it's actually still limited. Now let's think about other kinds of popular classical machine learning approaches like perceptron. In perceptron, one of the nice things about the perceptron is so-called universal approximation theory. Here, now perceptron is usually given by the linear layer with the bias term here, and there is a nonlinearity. And this is now linearly combined with the kinds of expansion coefficient here. Now, the nice thing about the perceptron is the space it can generate with this kinds of neuron is much larger than, I would say, the RKHS. Because, for example, here in this original theorem, you can say that any function in continuous space can be actually can be approximated with the perceptron with an arbitrary accuracy. It looks like a very nice result, but however, there is still limitation from the wish list we actually discussed before. For example, it turns out that even though this is actually can do that, the number of the neurons you require to approximate with arbitrary accuracy is become exponentially larger. Furthermore, if you actually train the neural network, this can be adapted with the new data, but however, this expansion coefficient is fixed during the runtime. So because of that, the expressivity is still limited. So now let's think about classical signal processing approaches using the frame expansion. Frame expansion is usually representing this one is a linear basis. For example, the dual frame and the frame expansion coefficient can be actually represented as frames as well. For example, this is actually general kind of representation for shifting invariant spaces. So because of that, this expressivity, the function it can represent is quite large. So it's a quite expressive representation. However, this is not a machine learning approaches because there is no learning going on. Once everything is just like a fix, and then you are now using this. So there is no learning. This is just linear representation. But if you combine this one with some nonlinearity like a compressed sensing approaches, now this become a machine learning approach. In fact, this is a shallow machine learning approaches. So here the main idea is usually the expansion coefficient of the frame is usually sparse. Only non-zero coefficient is sparsely distributed. So by utilizing that, you fit into this data to the measurement and also representing the sparse coefficient. And by doing this kinds of iteration, this is in fact the basis for Schur algorithm. And you can find the nonlinearity to find the shrinkage, this kinds of expansion coefficient. And based on that, you can choose the non-zero coefficient, the basis corresponding to the non-zero coefficient. So because of that, this is actually now, given the data, as you can actually find this non-zero basis in some adaptive manner, then this is actually the shallow machine learning approach. However, this has still limitations as well. For example, still the basis of frame representation is actually coming from the top-down mathematical model. You actually, depending on the function space you want to represent, you usually start with some kinds of basis, for example, wavelet basis, okay? Furthermore, another serious problem is it's transductive in the sense that the learning itself is actually given for the measurement. Optimization needs to be solved for each measurement, but there is no way to utilize these kinds of learning from specific measurement data to new data if you actually have a new data. So that means optimization algorithm should be solved at every problem. So it's not inductive model. So the summary we have discussed so far of the classical machine learning approaches, this is actually, for example, kernel machine, it's an inductive and also learning approaches, but still in terms of expressibility and the data-driven model, it's not. Same thing, single layer perceptron has many advantages, but still it's not actually expressive enough. And for example, if you combine with the frame with the compressed sensing approaches, yeah, still you can actually make an adaptive expansion or expressiveness, but the problem itself is not inductive. And furthermore, the basis and the frame choices is not data driven. And so that means this is still limited. Now, actually, now we talk about another class of the one, which is directly linked to the machine learning, the deep neural network approaches, but this is more like intermediate version of the neural network approaches. This is actually the what I call the deconvolution of Framelet expansion we actually published in 2018. So in order to understand this, we actually need to think about the convolution, the Hankel matrix representation of convolution operation. For example, this is convolution operation. Now this is actually represented as a Hankel matrix. Hankel structure looks like this and multiply with this kind of features. Now, one of the nice things, which is actually the work from the Yin et al. From the English Dobich group in the Duke University, what they actually find is this Hankel matrix can have a very nice decomposition. For example, here, now they define so-called the non-local basis and local basis. The reason it's called a non-local basis is because this Hankel matrix is usually tall. So this is multiplied from the left. So that means it's actually multiplied from all the pixel values. So this is non-local. But on the other hand, if we multiply from the right, this is also interacting with only small set of the pixel. So this is a local interaction. So if you actually define this kind of basis, non-local and local basis, what they show is like this. Now for any kinds of functions, they can actually present this one as a frame expansion with this kind of framelet basis, frame and dual base, frame basis. So in fact, actually here, this one is actually coming from the columns of the local base, non-local basis, and put size coming from the local basis. Now this basis, the frame is now as a convolution of the two. So that's why they call this is actually combining the non-local and local together to actually extract a better representation. So, and now we have, this is actually type frame representation. Now, one of the nice thing about this one is now this become a data driven. If you actually combine this one with the regularization term like this, and from the data, you can actually estimate usually, especially this filter part. This is actually usually fixed. Non-local part is usually fixed, but this local part is estimated from data. So if I estimate the data, this is a data-driven model. However, still expressive is limited because usually filter size is small, and also you need to compute the optimization algorithm. Now, in fact, actually, our contribution in the SIAM paper in 2018 is actually we demonstrate that this expansion has a very nice link with neural network approaches. For example, we start with the same kinds of non-local and local basis, but we can identify this one as a pooling-related layer, and this is a convolution fit. Why? Now here, we start with this Hankel matrix. Now we have a trivial identity by multiplying this one to the left, and then multiplying this one to the right. Now, if actually decouple, if actually define this one as a C, you can actually have this kinds of equivalent representation. But interesting happened after this. Now, Hankel matrix multiplication of this one is in fact a convolution operation. So this is a convolution operation. Now, after the convolution operation, this is an image, and now you're multiplying with some matrix, with a global matrix. In fact, this is actually exactly the same as a pooling operation. So in fact, this is an encoder part of neural network. Now, same thing, if you actually make this one an original domain, this representation changes like this. This is now unpooling layer, and this is now convolution layer. In fact, this is the equivalent form of the decoder layer in the encoder-decoder structure. So based on this kind of understanding, now this one gives us some kinds of insight, what kinds of like a signal processing diagram you can actually obtain depending on the choice of the pooling layer. For example, here, if you choose identity matrix here, you end up with this kind of encoder-decoder structure. It's a single resolution network. And you can actually cascade it in this way as well. Now, if you actually choose Wavelet, for example, in that case, you end up with this kind of neural network architecture, this kind of signal processing diagram, as you can see here. It looks like a very similar to the unit type of architecture, except there's additional high-pass branches here. Okay. So that means that actually, guys, depending on the choice of the non-local matrix, the network architecture is determined. So that's actually one of the important link we can actually find from here. However, this representation is a little bit different from the original convolution Framelet expansion. So where we can actually, how we can restore the original Framelet representation. It turns out instead of doing the matrix decomposition, if we vectorize these feature vectors in a one-dimensional vector, and then represented everything together with respect to this one, you end up with this kind of frame-like representation again here. Here, what happens is now this X is the input of the input images here, and Y is the output signal here. Now it turns out this analysis basis or analysis frame is coming from the encoder part of neural network, and this synthesis basis and dual base frame is now coming from the decoder part of the network. So in fact, this is not a high-level description. We have a close-form presentation of the basis. For example, we start with the linear cases. This actually, so far we discussed of the linear cases. There is no nonlinearities in the network. In that case, we can exactly show that this BI basis for the frame and the dual frame is now coming from the ith column of matrix cascaded matrix multiplication here. This EI is an encoder matrix at first ith layer, and same thing decoder matrix at the ith layers here. Now, furthermore, you can actually see the nice structure of the encoder and decoder matrix here. For example, this is now convolution with the pooling matrix with the filters. This is actually exactly the same thing we actually observe in the convolution Framelet representation. The convolution with the non-local and local basis is now represented in this way. And furthermore, usually this pooling is a fixed layer. We are now determining that at the beginning for the network structure, and this is learnable. Now, what happens if you actually have a skip connection like this without any nonlinearities? Still, the expression is exactly the same. Only difference is because of the skip connection, we have additional paths, and because of that, we can actually have additional block of the matrix, as you can see here. Okay, so because of that, what happens is now this become a redundant representation. Usually in the frame theory, if you have a redundant representation, it's robust to the noise, and a lot of advantages. In fact, this kind of skip connection gives those kinds of advantages as well. Furthermore, now you can actually say this is a really Framelet representation if you actually impose this kind of frame condition for the pooling layer as well as the filter layer. For example, if you actually have an encoder and decoder pooling layer as satisfying the invertibility condition and filter layer like this, then what I can show you is now this is satisfy the perfect construction condition, similar to the wavelet frames. So now here, but usually what happens is now this learnable filter is difficult to satisfy this frame condition, but you can actually make this pooling layer, because this pooling layer is chosen a priori when you decide the neural network architectures. You can actually choose this neural network architecture to satisfy this kind of frame condition. And based on that, there is some hope you can actually make this one as satisfy some kinds of conditions as well. Okay. However, this perfect reconstruction condition is not what we need. If we can combine this one with like a optimization algorithm with the regression term, you can do again. This become a more expressive representation because we have a multiple layer, so the filter span is become filter receptive field become larger. So it's become more expressive representation. And also it's a data-driven because the filter is learned from the data itself. However, we need to solve this optimization problem for each measurement data. So it's not inductive. So this is computation expensive operation. So the question is now, yeah, the convolution Framelet with the regularization term has many similarity with the neural network architecture, but still this is not an inductive model. So the question is how to make this one inductive. In fact, that's actually why the nonlinearity is very important. In fact, without the nonlinearity, there is no learning going on, and no, especially no inductive learning can be achieved without the nonlinearity. This is actually the message I'm going to talk. So why this is the case? Now what happens is like this. For example, if you have a Lelou nonlinearities, this expansion coefficient this expansion is exactly the same form. Only difference is in between encoder matrix, there is a diagonal matrix which is now determined by the Lelou activation pattern. This is a 0 and 1 diagonal matrix. If Lelou is active, this becomes 1. Lelou is inactive, this becomes 0. Okay? Now you can see what's going on inside of the neural network. Now, once neural network is trained, this encoder and decoder matrix theta is fixed. So because of that, everything is fixed. But however, depending on the input data, this Lelou activation pattern changes. Because of that, the multiplication with the Lelou activation pattern and the total matrix itself changes depending on the X. So that's why I have an X dependencies here. Now, because of that, this frame basis BI and B tilde also changing depending on the X. So now this we can actually see that why this neural network changes even though the theta is fixed, but still this is inductive because everything is just calculated, only changes this kind of Lelou activation pattern, and this is very computationally efficient. Okay. Furthermore, another thing you can actually think about is now this Lelou is after the convolution layer. Because the convolution layer is a linear, so linear it decides the linear hyperplane. So because of that, you can easily see that what's going on inside the neural network. For example, this is an input space, simplify the input space. Let's think about this is R2, two-dimensional cases. Now, in that cases, now, for each neuron, it determines the partitions of the space. And the next layer, it also defines the partition and something like that, cascaded partitions. Now, what happens is, within this partition, they share the same linear representation, like or frame representation, but across a partition is different. So because of that, what happens is if you have a new, different kinds of input data is coming, it chooses a different kinds of basis representation automatically. So what neural network is in fact doing is now CNN performs automatic assignment of the distinct linear representation depending on the inputs. So basically this is a basis pursuit algorithm, but instead of calculating the optimization algorithm, you are basically choosing this basis automatically based on the Lelou activation pattern. So that's actually where the inductive learning comes in. So once you train it, only changing is activation pattern. Because of that, we are now basically neural networks multiplexing based on this kinds of activation pattern to specific representation. So that's actually what's happening here. However, the partition geometry is not, even though I show here this one is some kinds of like a independent partition, but in fact, what happens in the neural network is partition geometry is a little bit more complicated and also even dependence. But that's actually where the very interesting behavior coming from. For example, here, this is a two-layer neural network. In the two-layer neural network, for example, this is actually the partition boundary from the first two neurons in the first layer. And this is a second layer neural network partitioning. Now, if you think about D layer, in that case, first neuron can be inactive in that layer. In that case, we don't need to do any kinds of partitioning anymore. But in B and C region, there is only one neuron active. So there is a partition direction is one direction. And this is actually in this region, two neurons are active. So we have independent two-dimensional partitions, as you can see here. In fact, you can easily calculate this one using simple two example. For example, let's think about two-layer perceptron with the two Lelous here, and the two-dimensional, this is R2. Now this weighting parameter is W, and there is a bias term here. Now let's think about some example. For example, this is some two example. So here, this is the first layer perceptron weight is 2, -1, and 1, 1, and this is 1, -1. And the second layer is 1 like this. In that case, if you actually calculate this kind of partition geometry, you can actually see this kind of nice, interesting geometry. In fact, this is very easy to solve. In fact, this is actually coming from my actually, I give the final exam to my students undergrad students last week, and this is actually coming from my exam solution. So in fact, undergrad student can easily, not easy, but still calculated it, okay? So anyway, so this is actually the first partition from the first neuron, but this is coming from the second layer neuron. Now, what happens is, now we have a very interesting happen here. Now in this first neuron, you can easily see that everything is mapped to the 0 and 0. So basically, if input coming from the input in this layer is coming given as an input for the neural network, the output will be 0. This is a length of this one is, length of this mapping is basically 0. So this is a 0 length mapping. Now in this region, you can see that the mapping is now given by XY coordinate given by just like one of the coordinates is 0. So it becomes a length 1 mapping, as you can see here. So the length of this one is the mapping of this one is length 1 mapping. Now, however, in this region, now the mapping is a 2-dimensional mapping. So this is a full length mapping. So in fact, this is what's going on inside the neural network. So for example, if you train the neural network, the partitioning gives a specific length, low rank projection, gradual varying low rank projection inside the input space. For example, if for some other reason, the basically neural network going out, removing everything, and some other reason is basically doing some full length projection. It's just like a transform. Otherwise, in the boundary of the region, there is a gradual change of the length. So basically low rank projection. So that means, for example, this region is more like a noisy images. In that case, by doing the low rank projection, you can actually remove those kinds of noises in the input image. So that's actually what you understand what neural network is doing from this kind of diagram. And furthermore, what you can see here is now the expressivity of neural network is directly related to the number of partitions, because each partition has a different kinds of linear representation. So the expressive of neural network is how many different linear representation you can represent it. So it turns out that maximum number of partition you can actually obtain from this kind of neural network is now depending on the number of channel. The number of is also increasing exponentially with respect to the number of channel. With respect to the network depth, you can actually show that number of partitions increasing exponentially as well. Furthermore, if you have a skip connection, the number of partition is also increasing exponentially. So that means neural network has a potentially a lot of very expressive and representing a lot of different kinds of mappings from the same neural network itself. This is a very good point. However, there is a very interesting behavior people also find from actual empirical data. This is actually coming from the work in the Listen I Clear paper. So what they do is actually they investigate the partition geometry when they train this one using the MNIST dataset. Now here, this is actually vanilla neural network for the MNIST classification. This is actually partition geometry. This using exactly the same network, they add a batch normalization, they have this kind of partition. And also, if you add a dropout, they have a different kinds of partition. And in fact, also number of partition, usually they found is not as many as exponentially many. Usually, it's actually much smaller than those kinds of the maximum of partition you can expect. So why this kind of thing happen? In fact, this is actually the very nice thing about the neural network. Actually, even with the same network architectures, depending on the complexity of the data, manifold, input data manifold, it can actually adjust automatically such that we don't need any, if you don't need any kinds of lot of partition, in that case, we can just simplify that one by doing that. Why this kind of thing? You can actually see also from the toy example. This is actually coming from our student final exam as well. Now this is actually what we saw before here. This is the first layer and this is a second layer neuron. Now you have this kind of partition geometry here. Now instead of doing that, and you change the second layer a little bit like this, it turns out the resulting partition become only 4 partition, as you can see here. If you compare this one, only changes this one number in the weight parameter and the bias sum, but still we have a very different kinds of partition as like this. Now, for example, here, this is a rank 0 partition here. Everything is mapped to the just point here. Now in this region, this is a rank 1 projection. So input data is now projected to the rank 1 output. So this is basically denoising area. And this is now transform area. This is a full length projections. So now based on the same neural network, depending on the data type or manifold type, sometimes this kind of complicated network is necessary. But however, if data is simple, you don't need that one. By just simply changing the weight parameter, you can actually have a much simpler geometry, as you can see here. So this is really what's going on inside the neural network. So based on this kind of understanding, you can see that deep neural network satisfied all the desired things we actually mentioned before. So it's a data adaptive model, and adaptive, and expansion coefficient is also adaptive as well, and very expressive representation. Furthermore, it can be number of expressivity is also determined by the data as well. And also it's inductive. We just changed the LeLu activation pattern, and based on that one, you can actually have a lot of interesting behaviors. So that means deep neural network can be considered as an ultimate, I would say, learning machine. So that's why the neural network is very powerful. And that's why there are a lot of exciting mathematical problems in the deep neural network. And actually, I show you some of the more interesting observations we have found, for example, regarding the LeLu. For example, in the LeLu, if actually the LeLu nonlinearities, what happens is, yeah, this is a neural network is a very complicated nonlinear system. So if we calculate the Lipschitz constant for the neural network, it's very complicated. However, if we utilize the LeLu, what happens is we can show that the Lipschitz constant is now determined the maximum value of a Lipschitz constant of each partition. Basically, this is a linear region. So maximum of the Lipschitz constant for each linear region is determining the total Lipschitz constant continuity of this neural network, which means that, in fact, this deep neural network is a piecewise, even though it's a nonlinear, piecewise is a linear system. That's very important advantage of using LeLu. But however, if actually use different kinds of nonlinearity, this doesn't happen. So calculating Lipschitz continuity is very complicated. You cannot have this kind of cross-form expression anymore. Furthermore, another advantage of utilizing LeLu is actually coming from the backpropagation optimization as well. For example, in the backpropagation algorithm, you usually have a forward propagation path and a backward propagation path. Forward propagation of the input and backward propagation of the error. And this weight update is now coming from the cross product of this input, output, as well as error backpropagations like this. Now what happens is, if you actually calculate the backpropagation, you end up with this kind of representation. Here, this is a filter layer again, weighting parameter. Now this lambda is actually coming from the derivative of nonlinearity. Okay? Now very interesting about the LeLu, which is not observed in other nonlinearities. Now the implication factor, weighting factor from the LeLu, this is an output LeLu value with respect to x, as well as this derivative is equivalent. So this is actually the same. So because of this important properties, what happens is this LeLu backpropagation becomes symmetric. So that means you have propagation and backpropagation, but now backpropagation nonlinearity is exactly the same. Derivative of nonlinearity is exactly the same as nonlinearity itself. So because of that, this becomes symmetric. So why this symmetry is important? If actually design this kind of optimization algorithm for each layer to obtain this kind of weight parameter, this become now positive semi-definite. You can by choice, because of that, with a sufficient small size of update, you can actually guarantee that this is now always the weight is decreasing, the cost is decreasing. Because of that, if with the LeLu, it's more stable to actually train the neural network. Okay. Now, based on this kind of geometric understanding, now we can actually think about various kinds of answer various questions. For example, based on this understanding, we can actually answer the question, which domain is good for the learning? For most of the cases, people think that image domain is the domain we need to train the neural network, because the reason is early CNN from Jan Nakoni is actually coming from the inspiration from the brain. So in the brain, for example, if some people see that, then some of the early layer has edge detectors. And if we go further and further, a higher level of concept can be inverted. Because of that, neural network is modeling this kind of brain. So they argue that this is actually why the deep neural network is working. And so that's why it's better to implement this deep neural network in the image domain. That's actually a common belief. But however, based on understanding that deep neural network is nothing but the signal representation, we're using like a, as I discussed before. In that case, the better representation is a domain you can actually represent the signal more effectively. For example, this is actually why we actually developed so-called case-based learning. So this is actually Fourier domain deep neural network approaches for the ML cases. For example, here before we actually working on the deep neural network, we actually work on the compressed sensing approach, especially the low-rank Hankel matrix approaches. The reason for that is we discovered that in these papers, if image is sparse or can be sparsified in the image domain, the corresponding Fourier domain data, if you construct the Hankel matrix, it has a low-rank structure. So because of that, Hankel matrix decomposition is directly related to the convolution framelet expansion. And because of the link, then you can easily see that instead of doing this Hankel matrix decomposition, we are now replacing this one as a convolution neural network. And based on that one, you can do the end-to-end training. And now this CNN is basically learning the interpolation kernel in the Fourier domain. It turns out this works very well and a lot of advantages. For example, this is actually the compressed sensing MRI application, accelerated application. This is accelerated image, and this is image domain learning and compressed sensing, the case-based learning approaches. Now, if you magnify that one, you can clearly see the differences. This is image domain. There are still remaining noises here. Compressed sensing is cartoon-like artifact, and the case-based learning is very closely related to the ground truth imaging. And also, my clinical collaborator said that there is a several vein they can see here, but in other images they cannot see that. Furthermore, case-based learning is actually very good for a lot of artifact removal in the MRI. For example, one of the important artifacts in the MRI is so-called EPI ghost correction. So EPI ghost correction is coming from that odd and even echo is not aligned. So because of that, case space's phase is shifted. So we need to actually calibrate this one using the calibration data. But as I mentioned, we used to work on the Hankel matrix approaches. What at the time what we did is now we are splitting the even and odd echo separately, and then convert this one as a compressed sensing problem because they share the same images, and using the joint sparsity, then is low-rank matrix Hankel matrix approaches can actually interpolate this signal, and then based on that one you can actually estimate the images. Now the main idea here is now instead of doing that, you actually replace, as I mentioned, the Hankel matrix decomposition directly related to neural network. So you can just replace this one as a neural network case-based learning and then train it. Now, this is a result we actually demonstrated in the 70 MRI. This is a ghost image. There is a Nyquist ghost, so there is a N over 2 ghost. You can actually see this kind of ghost images like this. Now, standard approach is you are now acquiring a reference signal separately, and using that one, you can actually calibrate the data. Calibration data. But still there is a remaining ghost here, and this percentage, a big percentage is not a good one, GSI value. And this is other compressed sensing approaches. Now this is actually our method. You can clearly see the number is significantly reduced and image is very accurate, as you can see here. Furthermore, utilizing this one, you can actually think about all different kinds of deep neural network in different domain based on the domain expertise you can think about. For example, another thing we actually investigate in the CT reconstruction is differentiated backpropagation domain learning. What do you mean by that? For example, in fact, there is in the early 2000s, there is a different kinds of CT reconstruction algorithm emerges from the helical CT reconstruction problem. For example, previously we know the filtered backpropagation approaches. We are doing the length filtering first and then do the back projection. But the problem of this approach is, for example, if you detected truncated, for example, ROI imaging, just imaging the ROI cases, because of the detected truncation, if you calculate the length filtering, then there is a singularity at the boundary. And the image, you can see this kind of singularity images. But backpropagation filtration algorithm is now coming from the differentiated backpropagation idea. So that means you are doing the differentiation along the source direction and then do the back projecting. then you end up with these kinds of images. Now there is some kind of one-dimensional lines here. It turns out if you actually calculate the Hilbert transform along this line, you end up with the correct data if you have no noises at all. So now what happens is differentiated back projection. The remaining part is basically Hankel Hilbert transform, which is basically the convolution operation. Based on this operation, now we know that CNN is basically learning the filter kernel. So instead of using the image domain data or the sinogram data, we start with this differentiated back projection data like this, and then learn the filter directly. That's much more efficient. It turns out this is very successful. So in our paper, we demonstrate it like this. Now we train the neural network once with a small number of set of the ROI sizes. For example, this is a very magnified view, and this is whole view here. This is only very small area imaging, okay? Now, if I just do the filter back projection, because of the detector truncation, you end up with this kind of the singularity at the boundaries here. Now, type 1 neural network is now, instead of doing that, you start with this one as an input and learn the clean image output and then train the neural network. Now, the problem of that one is that works with the specific ROI size. But however, if we change the ROI size, now this doesn't generalize well because of the singularity. You can actually see there is some remaining artifact like this. But however, if you train in this way, this is generalized very well. Now with the one neural network from different type of ROI, you can actually see the very accurate image reconstruction like this. Same thing happened. For example, here this is a Conebeam reconstruction problem. Now there is a circular trajectory. We have a very wide detector here. This is rotated along this direction. Because of the wide detector, it does not satisfy the reconstruction condition, what they call the twist condition. So because of that, if you do the standard reconstruction, there is an artifact here. That there is this image pixel value is now shaded, like a shading artifact in the top and bottom part of the images. And the image is deformed like this. Now, what happens is you can use the same kinds of idea and learning the DBP domain as well. In fact, there was in 2008, there was a very famous, very important paper. What they do is, in this kinds of Conebeam geometry, if you do the back projection first, and then in the back projection fit domain, if you actually find this kinds of plane in this coronal direction or Sagittarius direction, what happens is now the relationship with respect to original image to the measured differential back projection is now a filtering operation with the the Hilbert transform, but now this is a spatially bearing filtering operation. Now, neural network is very good to learning spatially bearing filter, so you can now learn the neural network in this domain as well. So this is what happened. This is ground truth image. Now this is standard reconstruction. You can see this is shading artifact and the image is deformed. And this is compressing approach with the total variation. Now you can see you still have a remaining artifact like this. And this is now image domain learning, the standard method using the image domain and train as a ground truth. You still see that deformed images. The shading artifact is reduced, but image is deformed compared to the ground truth. But now if you actually do our method, now you can see that this is a clearly accurate reconstruction. Same thing happened in the corona view, the axial view. All these kinds of artifact is completely gone in this kinds of approaches as well. Now another thing is actually the wavelet directional learning, what it said. This is actually very, and in fact, this is an unsupervised learning approach. So I'm not talking about unsupervised learning here, but this is also, instead of learning in the image domain, there is a better domain you can learn based on this understanding because the domain signal representation is better. This is actually motivated from our project with the national, the Korean Aviation Research Lab. What they actually have this kind, they have a satellite system, but they actually have, of course, the commercial satellite, and they many of the sensors has there is sometimes depending on the condition, they have some kinds of artifact you can see. Like this. This is a banding artifact, a stripe artifact, and this is a horizontal artifact. But the problem is that this is not deterministic. This location changes depending on the condition and depending on the pattern changes depending on that. So the problem is there is no ground truth in this kind of cases. So we want to do some kinds of the unsupervised learning. But unsupervised learning is not my focus here. But our goal is like this. What I found is instead of learning in this image domain as people do, it's better to actually learn in this based on the property of the signal. So what I did is like this. We are doing the wavelet transform. And then if we do the wavelet transform, now here, there is some domain artifact is more visible because this has some specific directional pattern, as you can see here. And this is more like a horizontal dominant, and this is vertical dominant. So now you are just like using those kinds of band and then do the inverse Fourier transform, inverse Wavelet transform. You end up with this kind of images with the artifact plus some of the signal. Now the goal is now utilizing this one. This is actually better representing the signal. So why not utilizing learning the neural network in this domain? So you are now using this one from the noisy data and the clean data, and you are now trying to estimate these kinds of patterns, and then estimating the noise pattern and removing it. So this is our plan. In fact, actually, as I mentioned, we don't have any kinds of pair data. So we actually implemented this unsupervised learning with the scikit-learn architecture. I'm not talking about the Theore because actually there is also very important and very interesting geometry about based on some kind of optimized transport geometry about scikit-learn. In fact, actually there's another webinar I'm supposed to talk in next week. So there I'm mainly talking about unsupervised learning and optimal transport geometry for that. But at the time I talk about more detail. But here I'm just showing this image wavelet domain is better. So here this is a result. This is actually the real data we obtained from the agriculture area. For example, this agriculture area, this is the blue area is our reconstruction result. Now this is all the existing method here. Now here you can see some of the remaining artifact or blurring artifact. And in that case, this is much better. And this is actually the cloud area. Cloud is more like a text-like patterns. And in the older reconstruction area, there is still remaining banding artifact like this. But our method, you can actually clearly see that everything is completely gone. Here, this is actually the ocean area. Now this is actually the simulated data. We have a ground truth data. And now this adding this kind of node pattern. Okay. Now this is all our algorithm. And now this is our result. You can clearly see that most of the patterns are gone and only small signals are just remain, and everything is actually very, very similar to the ground truth. And this is a real data from the ocean scene. Now clearly see, you can see that our result is much better than compared to other results. So then based on this understanding, so what you can say, we can answer this important question: what does the CNN learn? In fact, this is actually the picture which is analog to the first picture I showed that for the classification cases. So in fact, we can say that classical regularized reconstruction approach like a compressed sensing, this is actually compared as can be said as a basis learning approach. So we need to actually have a top-down basis model and then doing the optimization algorithm to do the basis learning to choose optimal basis to have a good result. However, deep neural network is doing, we don't need the basis engineering anymore because deep neural network automatically find the correct basis from the training data. And also among the bases, you choose appropriate basis by changing the Rayleigh activation pattern automatically. So we don't need any kinds of basis engineering in the deep neural network. That's why this is much simpler and much more effective. And that's about it. And thank you very much for listening.
Thank you, Jong Chul. So any questions? If you have any questions, you can click the raise hand button and then I will unmute you. Any question from the audience? Yeah, I have a question. Well, it's a very interesting talk, and so especially the connection of type frame and deep neural network. So if I understand correctly, so these well, at least in the pooling part, so the basis is fixed, right? So is it the phi function, is it fixed? It's not learned, right?
So it's actually fixed. It's
Yeah.
actually a fixed one in the usual neural network cases because fixed.
Yeah. So then my question is, so because in type frame, so there are many type frames that give a different order of approximation. So if I play around this, can I get a better CNN deep neural network?
Yeah, that's what I get. For example, here I mentioned about this kind of wavelet domain learning is in fact actually you can actually combine. This is basically what we can think about. Yeah, this is a little bit different, but this is basically we are utilizing those kinds of property of the type frame to extract the signals and then learning after that. You can think about it in that way.
Okay.
Yeah.
I have a question, Jong Chul. That illustration with the simple example was very interesting, or the one that you gave as an exam question to your students.
Yeah.
But I also see that as a potential for, because of the complicated regions that it create, I see that as a potential for overfitting. How do you balance fitting and underfitting and overfitting?
Yeah, that's actually, I show you these pictures here. If you see this picture. Now this is the same neural network, 2-layer neural network with the 2 neurons for each layer. But now this kind of thing is actually much more large number of partition, but this is simpler partition. This is can be, for example, if actually your data is very simple, but you partition in this way, this is overfitting. But now neural network is amazingly what happens is if your network is simple, the data manifold is simple, in that case, it automatically chooses in this way.
I see.
Yeah.
There's a question, Raymond, in the Q&A section. Would you read that, please?
Well, I cannot. Sorry, I cannot see it. So
okay, let me read it. The question is from Hong Peng Sun. Thanks for a great talk. Could you please give more comments on how to learn FBP for CT?
FBP for CT?
Yeah, Hong Peng, we can let you speak if you like to answer the question directly. Go ahead and talk, please.
Okay, I'm very interested in how to learn the FBP because you need to do the inverse FFT, something like.
In fact, we don't do the learn. We do not learn the FBP. We just use analytic part as it is. That's much better. And for example, what people do is you're just doing the filter backprogression first, and then in the image domain, you can actually learn in the image domain using the neural network after the FBP. But here, what I show is not only that's the option. Instead of doing the filter backprojection, if you do the another analytic part, backprojection filtration, this is differentiation and backprojection. But rather than doing the Hilbert transform, if we replace this one using the CNN, we have a much nice generalities and better flexibility. That's my point. But this is actually just analytic part. Yeah.
Okay, thank you very much.
So I think the slides will be made. Can you make the slides available for the for the people who are interested?
Yes.
Yeah. Okay. You can maybe send it to us in PDF, and then we will post it along with your talk.
Good. So are there any other questions or comments? Okay. If no, then well, we are right on time actually. So let's thank Jong Chul Ye.
Thank you for a very nice talk.
Thank you for that. So very interesting and informative talks. And our next week speaker. So we still have one more talk before we go to summer vacation, wherever we can go. It's by Boris T. from University of Grenoble. Yeah. So hope to see you next week. Bye bye.
Goodbye.
Thank
Okay,
you.
great.
Thank you, Jong Chul. Bye.
Yeah.
Bye.
Bye.